Now let's talk about how to avoid saturating neurons and vanishing gradients. We will discuss issues that prevent networks from learning and solutions to these problems. Let's start by looking at the activation function tanh and the sigmoid function. This slide shows both functions. The blue curve is the tanh and the orange one is the sigmoid function. We see that if we move far left or far right, the derivative is near zero. As you can see, the curve is here horizontal. So we call that the neuron becomes saturated in these regions. Let's now consider what happens to back propagation. When we do back propagation, we take the derivative of the error times the derivative of the activation function. But if the neuron is saturated, so here in this areas and this areas, this derivative is zero, and that means the weights adjustment will be zero. That is, the network stops learning. Let's put this differently. When we are in the saturated region, a small change in the input will not change the output. Therefore, we will not adjust the weights, and we want to avoid this problem. Let's take an analogy. Tired student and the multiplication table. Imagine you are learning the times tables in year 2 or year 3. Your brain is paying close attention. Every new number helps you learn. When your teacher corrects you, you listen and change how you think. That's like your brain's weights adjusting. But then after practicing too much without a break, your brain gets tired. Even if the teacher corrects you, you don't really hear it anymore. You just stare and say, I already know this, even if you don't. That's like a neuron becoming saturated. Your brain is stuck. No matter what correction comes, it doesn't change. And for the back propagation part, when your teacher gives feedback, which is the error, your brain should use it to get better next time. That's what back propagation does. But if your brain is tired, saturated, it stops listening. So no matter how much feedback you get, you don't improve. That's why we say the network stops learning. Instead, we want the weighted sum to be close in the so-called active region, close to zero. And this at least in the beginning of the learning process to make sure that the weights get adjusted. So we want the weighted sum to be here in this region. We call it active region. If we compare the tanh to the sigmoid function, we see another difference. We see that the maximum derivative of the tanh is 1.0, while the maximum derivative of the sigmoid function is 0.25. This will impact what happens when we stack layers. Consider when we are back propagating the error through multiple layers. Every time we will multiply by the derivative of the activation function. When we do this with sigmoid layers, even if we are in the active region, which it has maximum value 0.25, every time we will multiply by the derivative of activation function, it will be closer to zero. Repeatedly, the gradient will slowly approach zero, even if we are not in the saturated regions of the neuron. This is known as the vanishing gradient problem. This explains why it's better to use tanh as hidden layers in the network rather than sigmoid. Let's take an analogy of vanishing gradient problem. Think of the gradient like a message being whispered from the last layer back to the first. If every person in the line whispers only a quarter as loud as they heard it, after 5 or 10 people, the first one hears almost nothing. That's exactly what happens when we backpropagate through many sigmoid layers. Let's recall that the derivative of a curve tells you how steep the curve is. In other words, how fast it's changing at a given point. Just this is as a reminder. Now, how can we mitigate the saturated neurons or the vanishing gradient problem? There are some techniques like input normalization, batch normalization, weight initialization, cross entropy loss function, different activation functions instead of sigmoid. The first three will be discussed in this video and the others in other videos. All of these techniques either reduce or avoid saturated neurons and vanishing gradients. Some techniques only apply to specific layers, such as the input layer or the output layer, whereas other techniques can be used for the hidden layers. I will start with the input normalization. We saw on a previous slide that both the sigmoid and tanh neuron can saturate on both sides. This happens when the inputs to the neuron is of large magnitude, as you can see here in this slide, here in this area and this area. Let's consider the first layer in the network. Here we can avoid saturation if we make sure that the input values themselves are close to zero. This will imply that the weighted sum is closer to zero. We can do this by adjusting the input values, something known as normalization or standardization of the data. There are many methods. Let's start with a common one, which is to scale the value to be between 0 and 1. In cases where we have the input data as a grayscale image, we know that each pixel is between 0 and 255. We can simply divide the value by 255, which will result in a number between 0 and 1. Another common technique is to adjust the inputs to a small value centered around 0. This is known as standardization in the statistics community. We compute the mean of and the standard deviation of the inputs. And this is very important to compute the mean of the inputs. We then subtract the mean and divide it by the standard deviation. When we subtract the mean, the value will be centered around 0. The standard deviation is a measure of the spread in the data. A large negative or a large positive value will lead to greater standard deviation. If we then divide by the standard deviation, it means that all the values will get closer to 0. These are effective techniques to reduce the risk of neurons in the first layer being saturated. This slide shows code in Python how to do this using NumPy operation. We just call .mean and then .stand std for standard deviation. And here we subtract the mean and then divide it by standard deviation. The output will be standardized. The other technique is batch normalization. Even if we use normalized input data, we can still have problems with saturated neurons inside of the network in the hidden layers. This will much depend on the neuron types. If we have tanh, the output ranges between -1 and 1, which will reduce the risk of saturating neurons in the next layer. However, there are also neurons with unlimited output. They run a greater risk of saturating the next layer. We can mitigate this using something known as batch normalization, which introduces normalization operations between the layers. We will not get into the details of how to implement batch normalization. Instead, we will rely on the deep learning framework. The deep learning framework abstracts the batch normalization as a layer. As you can see in this figure, we see the batch normalization here between the weighted sums layer and the tanh functions. So between the weighted sum and the activation function. And this code snippet on this slide shows how to implement using TensorFlow. Just call batch normalization. This is another way. We applied after the batch normalization. We applied it after the weighted sum, after the activation function. So we applied the batch normalization here after the activation function between the layer and the next layer. The code snippet on the slide shows to implement how to implement this using TensorFlow. The third technique, weight initialization. Not only the input values will impact the weighted sum, it will also depend on the initial weights for the network. If the weights are closer to zero, the sum will be closer to zero, and that reduces the risk of saturating the neuron. If we assume that the weights can be both positive and negative, and we start with random weights, we would expect that the average sum is actually close to zero. However, the amount the average deviates from zero will depend on the number of input weights. Let's consider a neuron that only has two inputs and that these weights are initialized to values between -1 and +1. And the inputs are also between -1 and 1. The maximum sum would be 2 in this case. However, if we have a neuron with 10 inputs, the maximum value of the sum could be as much as 10. That is, the more inputs to a neuron, the higher risk that the neuron will be saturated if we use a fixed range of weights. We can use this observation to derive a formula for weight initialization. There are two common methods. One is Hay initialization and Glorot initialization. The Glorot initialization is recommended for tanh and sigmoid neurons. Hay initialization is recommended for something known as ReLU neurons, and that will be introduced very soon in future videos. This slide shows the formulas for Glorot and Hay normalization. And this code snippet on the slide shows the example on how we can apply this initialization technique using deep learning framework. Deep learning partitioners usually don't have to focus on the exact formulas, but can simply rely on deep learning frameworks to implement these functions. As you can see here, we just say kernel initializer equals to Glorot uniform.